decided to go slowly because the construction is a bit involved, so we need to go slowly. So we will remind that. So we're going to begin with the definition of a Veltman frame. Veltman frame. These are frames for IO. So what is a Veltman frame? It is, of course, a tuple consisting of a set, a binary relation R, and now a system of binary relations labeled by elements of W. We assume it to be finite. And of course, R has the same meaning as in probability logic, so that's accessibility for box. And this SW plays a role for interpretability or conservativity relation. So what properties we assume? We assume that R is irreflexive. Or what is it conversely confounded, that's also fine. Transitive. There was
just a notification.
Relation for W, and for every W, SW is also a binary relation on W, but it is reflexive. Transitive. And de facto, it will be a relation not on the whole of, we will look at it as a relation on the whole of W, but de facto it will be a relation on the set R of X, right, of successors of X. So W defines for every, SW defines for every W certain relation on the successors, on the set of successors, which is reflexive and transitive, but can be different for different W, except that the following conditions are satisfied. So firstly, we of course have that if U as WV, then of course UV are X. Secondly, if W are U as WV, then U R W, V, and finally, if U as W, V, R, Y, then U, R, Y. So this condition is written here, but basically, but these two conditions add something, some non-trivial information. So this one is essentially that R is a subrelation of SW when restricted to R of X, R of W. On R of W. And this one means graphically this condition. So if we have this S arrow, SW arrow, from U to V, and then V is looking at a certain point Y, then there is a by transitivity. so these are formally all the conditions, and this of course corresponds to the Montagnier axiom. But let us define the validity relation. So a model, as always, is a Veltman frame together with evaluation of variables, and we define the relation the truth relation or forcing relation on this model by the usual clauses for variables. Usual for variables, Boolean connectives, and actually box. And for triangle, we will have the following. So we need to specify when the formula phi triangle psi is true at W. Denote W, and this happens if and only if for every U in R of W, if phi is true at U, then there exists a V also in R of W, of course, such that U as V, also with respect to W, and of course V validates psi. Like, so this is the kind of for all exists statement. So for all U, if something is true in U, then there is a V such that.
Oh, just to make this definition a bit symmetric in the antecedent, also you can quantify existentially over U, right? Over V's, right? If exists some V which is SW accessible to U such that that V satisfies phi, then there exists some possibly other V such that blah blah. Is it true?
Wait a second. So you want to say this, if
this
there exists some V,
or just to make it symmetric.
Some Y such that
I guess
in that Y, the problem is where do we require this V to exist? In the R of W or in R of that specific?
In R of W. Again, well, the same, exactly the same existential quantifier in the consequent could be added for free in the antecedent, I guess.
Yeah, but I actually don't see why that would be simpler. But okay.
Well,
I think this is clear.
It's well, the non-symmetric definition is a bit annoying.
Yeah, it's a non-symmetric connective. So what?
It is well. The antecedent and consequent are behaving similarly. Well, given the other axioms of the ILM, one expects that they would behave symmetric. Anyway,
well, maybe, but let's say in this form the meaning is again in the picture like this. So we have W, and in order to verify that this holds, we must check the following conditions. So for every U which is above R above W, we must be able to find the corresponding V, which will automatically be also R above this W, so that in V we will have psi, provided phi is true in U. So that's the point. Right. So that's the condition. And now we would like to in fact, prove this soundness lemma. In fact, lemma. That if ILM proves phi, then everywhere the formula phi is true for all Veltman models. All Veltman models.
Sorry,
Yeah. Yes.
can I see that? Well, can you remind us that what was the definition of box here? It was not phi triangle falsity, right? Or it is,
Not phi triangle falsity
and with this definition, it
is equivalent to
box phi.
box phi.
And via this definition for triangle that you provided, box is as you expect, right?
Right.
Okay.
And it should work like this. Let's have a little look at this. So this means that phi is true everywhere above,
Right?
and this means that if somewhere above there is not phi, we will be able to find something above where falsity
Which is
true, which
impossible.
never happens. Means that we will not be able to
Yeah.
find this node where not phi. So that's more or less one principle that is valid in all such frames. But it is also derivable from the axioms, which is also, we can also check that it is derivable. But
Okay.
again, so we have this easy soundness part, for which I would maybe do as exercise the M axiom. So clearly, this condition corresponds to this axiom that diamond. So two principal axioms, apart from a bunch of obvious ones, are the axiom that diamond phi, how do you call it, interprets phi, and another one was that if phi psi, and then phi box theta, triangle phi psi. So this is Montana axiom, and this is
Always.
axiom without a name. Okay, but important principle. So this one corresponds to this condition. Why so? So suppose we have a Veltman model in which, in some world, so suppose we verify this axiom in the world W. Then we must verify that for every world above U, which is above W, if in U we have diamond phi, then there is some node where we will find phi. But okay, so diamond phi means that there is something above U, also R above U, where we have phi. But both of these nodes are above W, so by this principle, WUV, we will have here also SW arrow between U and V. And so we have found a node where phi is true. So that's the verification of this principle. And this principle, let's see, so what this principle amounts to. Okay, so let's see. So suppose we have, again, W and phi implies, phi interprets psi is true there. So whenever there is something for every u, one can find a v. So that's what we postulate here. And what we need to show is that for every u, if in u we have phi and box theta, then there is a v in which we will have psi and box theta. Okay, so assume that we have here phi and box theta. Okay, so we know that because it is phi, so that there should be something where we have psi. Let's go to that node v where we have psi, and now we have to prove that box theta is also true here. But okay, so suppose we have here anything r accessible, some x which is r accessible from v, in which theta is false. Then there is an r arrow from u to x because of this configuration. See, here's the last condition. So that will be, we will have an r arrow here, and so box theta cannot be true here. Contradiction. So this is all very simple in some sense. Okay. Let's do the next step. So next step is simply to say that in fact theorem by de Jong and Veltman is complete. In other words, actually, the reverse arrow is also true. And this is a purely model logic result, which is, however, not so simple. Nevertheless, doable. So we will skip this whole part of the proof because there is no arithmetic in it. So the conditions are relatively natural. So everything happens naturally. Maybe there is some room for simplifications there, in the purely model part. But one can read it, for example, in the Handbook of Proof Theory chapter by de Jong and Japaridze, who actually prove this theorem, so including the model part. So you can read it there. But
yes, in which year this theorem was proven?
A good question. So I would say around 1986 or something like that. Pretty old. So it was proven, of course, before Japaridze and Shorokov, but not a too long time before. So Japaridze and Shorokov was 88, 89, so this must be maybe 86, 87.
Okay, thank you.
Mm-hmm. So, and now we are going to do the main result. So, arithmetical completeness. Let me remind what it means. So, I suppose that we recall that for every, let's say, model formula 5, we associate its arithmetical. So, if f is realization, in other words, a function assigning sentences to prepositional letters, then ft of 5 is the translation of phi, arithmetical translation of the formula 5, where we interpret box, ft of box psi goes to essentially provable in T of the formula ft of psi. like that, and ft of phi implies psi is of course the statement that psi is conservative over phi. In other words,
Okay, you mean P1 conservative, yes?
pi 1 conservative. So t plus psi is pi 1 conservative over t plus phi, or rather ft psi ft phi, like that, which is again expressed in terms of probability in t, right? And the truth definition for pi 1 formulas, because we need to say that for every pi 1 sentence, if it is provable here, then it is provable here. So this is altogether, this quotation mark is a pi 0 2 sentence. So that's the meaning of translation. And we would like to show that if ILM does not prove formula phi, then there is such a realization, arithmetical realization, such that t does not prove f t of phi, where we assume that t contains I sigma 1, and t is sigma 1 sum.
Sorry, just to, well, I'm a bit confused about the definition of the conservativity. Can you say it again, please? How exactly you mean?
Okay, for every, I write it semi-formally, right? So for every pi 1 sentence, if box t plus ft of phi pi, and then box t plus ft psi pi. Instead of plus, here you can write box t. Ft phi implies pi, then
Isn't the reverse?
Yeah, usually in the literature, but for instance, when one says that, for instance, piano arithmetic is conservative, pi 2 conservative over Heyting arithmetic, one means that if piano arithmetic implies any pi 2 sentence, then Heyting arithmetic also is implying the same pi 2 sentence. It is usually in this way. But you are,
right.
you are referring to the other way around, right?
So
just to make sure that...
Let me explain. So, and simultaneously check if I'm constantly confusing. So, in the most typical situation, you have a pair of theories, T and U, in different languages, right?
Right.
Such that T is contained in U, and then you say that U is conservative over T if it does not prove any U statement.
Yeah.
So here this containment part is absent. So we do not require that that
one is including the other.
Included in the other. So we simply say that T is conservative over, or U is conservative over T.
Gamma conservative for
gamma conservative or pi 1 conservative. U is pi 1 conservative over T if whenever U proves, and now should be careful.
Right. You're using the other way actually.
Yes, it is should be careful. So whenever U is conservative means that it does not prove anything pi 1 which is not in T.
So it should be T provable implies U provable.
Yeah, so
that's a containment.
U provable implies T provable. U provable implies T provable. Then U is conservative over
so
T.
in this case, psi and phi should be swaps, right?
Unless you just say
Right,
that
so,
just the
now,
reading
how do
should
we
be
do
changed.
it? So-
Psi is
so that's the meaning of the term conservative. So we,
Yeah.
I think we're clear what meaning of the term. Now we write it the other way around. So we write, so the meaning of the term conservative de facto means that T proves every pi1 sentence U proves.
right.
That in that sense, T is stronger than U because modulo
Everything that
Yes. So when we write it like this, then the theory which is conservative is on the right, and the theory which is conservative over is on
in the left. Yeah. So you should read it
So-
on the above.
So this one, this definition is correct. And now we should maybe correct this one and bring it into accordance with this. Right. So we say that if f plus psi, then f plus phi. Right. Like that. So now we are okay. And this is the translation of that specific
Right.
relation.
Okay. Actually, in last session also you used the same. Well, I wouldn't say
The
at
same
that moment.
confusion.
Yeah. Well, we discussed with Giovanni
Because
actually
there are
afterward.
too many inverses here, right? So we,
Yeah.
in Russian language, in English language, we say it in the opposite order than we write implications, right? So that's the most confusing part. So every time you tend to say that if something is conservative over that, you would write it like psi implies phi. But no,
It's in the other way around.
yeah, that's okay. Anyway, so thanks for the correction. So this is the translation, and this is what the theorem is saying. And of course, we will replace this assumption by using de Jong-Veltman. So if there is some finite Veltman frame in which phi is false, then we would like to say that there exists an assignment f such that, so our task is to produce, given a finite counter model, produce an arithmetical assignment and an argument that this is not true. So that's the idea. And as usual, everything begins with this picture of so we can always assume that W is the root of this model because everything reachable from the root is not reachable from the root can be deleted. Reachability is of course by composition of S and R arrows, but right, so that's the part of the model where phi will also be false. And the first thing we do, we add the new root to it, and in fact we consider that our model W looks like this. So this node will be, so the nodes will be numbered, this will be 0, this will be 1, and this will be some finite set of numbers, codes of these nodes. How do we arrange, so the R relation is clearly depicted here, and the S relation, of course, every SW corresponding to the upper part remain the same, and S0. So we say that X is S0Y if and only if XY are in this area R of 1, and then X is 0 in the old model, and or let me say or simply
Maybe S1, not S0.
1 S
X.
0. S0.
Oh,
S1
you're
is
just
already-
defining S0 by S0? Well,
Sorry.
yeah,
S1. S1.
right.
And or 1 are for x is 1. X is 1
And Y is R accessible to X.
and y is in R of x
Yeah.
union
Yeah, because it should be reflexive here.
Okay, well anyway, so that's clear. So how to arrange it so that it is still a model. An important thing is that nothing changes after the node 1. So when you model, the same formula is still true. Okay, so that's a technical preparation which is typical for all these constructions. And then what we would like to do is we would like to assign to every x here, so to every x we will assign a certain limit statement, therefore we denote it lambda x. Now, I used to denote it Sx for Solovay traditionally, but here S means the relation. So we need to rename this to, let's say, relation. Okay, so lambda x. And there are conditions that we want to meet. Let me. Okay, so let me. Maybe we will. I will keep writing here. These are the important conditions. And it is very nice that in these proofs one could actually isolate these necessary conditions. This way the construction, which is complicated, is split into manageable parts. So, okay. Lemma. So, there exists a family of these sentences lambda s, such that the following conditions are satisfied. So, how do we number them? Okay, let's number them A1. A1 is that this lambda x's are like, so in fact the part corresponding to box and propositional logic is exactly the same as in the standard Solvay construction, because what else could we require? Nothing else. So this is, but let me reproduce them. So the theory T proves disjunction lambda x W. T proves not lambda x and lambda y if x is not y. A2. So if x are y, and then t plus lambda x proves that lambda y is consistent with t. A3. If x is different from 0 and y is not above x, then t plus lambda x proves box t not. sometimes we formulate the same condition by saying that T proves disjunction for all the lambdas that are strictly above X. But in view of condition 1, it's the same thing to say that every one which is not in that set can be refuted in T. But this is not, it can be refuted in T under the assumption lambda X. So that's the tricky part. And this includes y equals to X because R is irreflexive. So lambda X implies box T, not lambda X. So that's one property. So these are the standard requirements as in Soloway, and now two additional requirements. A4, clearly corresponding to the triangle when it is true or false accordingly. So if U S W V, then T plus lambda W. Right, so here the idea is that we are now sort of assuming lambda W and looking at the worlds which are above W. So T plus lambda W proves lambda U T lambda V. And now you check whether I did not confuse left and right hand side of this. So, but basically, I think this should be the idea. In other words, so this is a variation of that part which I have erased. So in other words, lambda V is conservative over lambda U for pi 1 sentences.
Mm-hmm.
So that's the central condition, and this condition is somewhat more complicated, but also kind of explained. So suppose we have a set of nodes V such that for every V from V, U is not related by S to V. So we are in the situation that we are sort of sitting in W and looking at the world U which is above W. And then we have a certain set of nodes such that none of these nodes is SW reachable from U.
Mm-hmm.
Then we can say that T plus lambda U, lambda W proves not lambda U preserves pi 1 conserves lambda V for V. In other words, that this big disjunction is not pi 1 conservative over lambda U, provably in T plus lambda W. So this lambda W, it kind of complicates things, but this is our kind of running condition for all these requirements, right? So we are sort of sitting in a certain node X, assume lambda X, and then claim that something is provable. And so in this case, we can simply claim that conservativity is provable. And then in this case, we can claim that conservativity is disprovable. But what we need to disprove is not just the single statement lambda V, but rather the whole disjunction. So notice that there is a monotonicity here. So if disjunct. So this theory is conservative over this theory. So if the theory is weakened, then conservativity
Would still be.
becoming easier to prove, so to say, more probable in some sense. And we are proving negation of conservativity. So by putting disjunctions here, we
You
are
are
making
strengthening.
stronger statements. So maybe it could be, well, in fact, among such V, there are maximal ones, right? So simply, yeah, you can take all
Yeah.
the nodes, even the supreme. So take all the nodes
Which are not
which are
SW
not
accessible.
so the kind of maximal such V, and that will be the strongest statement that is required. So I don't know what he stated. There is a quantifier over V, but okay, so not much different. And A6, final condition that in the standard model, lambda 0 is
True.
true. Right, so this is kind of also, as one would expect. So the key thing would be, of course, now to somehow manage to achieve all these conditions simultaneously. And for this, a considerable modification of solving construction will be needed, which I consider maybe the most kind of advanced modification so far. But let's now first prove the theorem from these assumptions. Assume that we managed to construct these lambdas, then let's convince ourselves that everything works smoothly. That's again sort of easy, so let us do that. Okay, for this we need will need a lemma, standard commutation lemma, main lemma. But it can be called main lemma after we established the conditions, because in this case establishing the conditions is of course a crucial point. But now let's see that it works. So the main lemma is the following. So for every W different from 0, item A, if it's again the standard, if phi is true, so all in this fixed model that we are talking about, item B, if phi is false, then T plus lambda W equals negation. Right. So that's the lemma. So again, let's quickly recall the propositional part and the model part, because yeah, we did it with Japaridze, but this is therefore it works the same way, even simpler for this case. But okay, so if phi, so we proceed by induction on phi, proving simultaneously A and B. If phi is a variable, then yeah, we should have defined first the interpretation of variables, but this is standard, right? So we define f of p as the disjunction lambda x for all nodes x where p is true, and then we prove this main lemma. Right, so if phi is a variable p, and in W p is true, then lambda W simply is disjunction of where. So then lambda w occurs in this disjunction, so it implies the disjunction. And item 2 is proved in the following way. So this is a big conjunction in which W does not occur, and by condition A1 part 2, it holds. Now, A and B clearly commute with negation, and they also clearly commute with conjunction because of the structure, so to say, of provable conjunction is equivalent to provability of each of the conjuncts. So Boolean part is easy. Now the modal part, we can actually skip it. Formally speaking, as we know that modality is expressible in terms of triangle, we could simply ignore this whole thing. But basically it would work exactly as in Solvay. So how would it work? So if, so for example, if phi is the formula diamond, suppose phi is a formula box. Then item B tells us that there is a node above W, let's say V, where this box psi is false. So if W falsifies box psi, then there is a V in R of W such that in V we have psi. Then we will have to apply induction hypothesis item B for V, and we will have that T plus lambda V proves not F psi. And then we do transposition, right? Then from this we can infer that diamond lambda okay. Let's say then we infer that Ft psi implies not lambda V, then box T Ft psi implies box not lambda V, and then transposition again, and we see that not box not lambda V implies not box T Ft psi. So all this is then provable. And we see by the condition number 2 that from lambda T plus lambda V proves actually the premise. So it proves the conclusion. And this is what we need to prove. So that's the case there. And the case for A, so suppose W box psi is true, then we say that for every V in R of W, psi is true in V, then we can claim that lambda V implies Ft psi for every such V by induction hypothesis, and then we claim that the junction lambda V for V in W implies Ft psi. So that's the crucial part. Then we can put box into it, box using the usual principles, so V in R W. And then again by this condition, as I remarked, we actually have that t plus lambda v implies that it is provable that lambda is above v. So it cannot be outside this cone above v, because this is precisely what this condition tells you. So that's how the Solvay, standard Solvay construction works here. So we verified A and E for boxes. So with this, it kind of, but we could have skipped this verification simply for the reason of, as I mentioned, box is reducible to diamond, to triangle. So now we come to the more central part with triangle, and let's first prove the following property. So claim. Right. So assume that phi is now phi 1 triangle phi 2. Phi 1 triangle from phi 2, and okay, and we denote by Fy the set of all nodes where the formula phi I is true. And we consider only the nodes above W. So we consider nodes X above W where phi 1 is true and phi 2 is true. So these are two sets. And the claim is that, of course, we have this claim. That T plus lambda W proves that Ft of phi I is equivalent to lambda x in Fi. So, assuming lambda W, so we, as always, we assume that we are living in lambda W, and then what we are claiming is that from lambda W, these two things are provably equivalent. So the formula phi I is provably equivalent to this disjunction of the corresponding lambdas. This is a kind of, so we, since we are within this argument by induction on the construction on phi, I mean, we have already verified these properties for the formulas phi I. So that's what we have, and now we more or less would like to if you like, simplify the arithmetical interpretation of phi I to such a disjunction. So, formally speaking, we need to argue here, but it's not a big argument. So, firstly, we can always.
Excuse me, I'm a bit confused here. It is not possible to prove in general that for any W that T plus lambda W is implying the equivalency of Ft of phi is equivalent to the disjunction of all lambda x's such that.
Where? If we are talking about the whole model, then yes, by the lemma that we are going to prove. But now we are talking about sets Fi, which is referring to the set of nodes above W, and we are assuming lambda W. We are not in the outer world. We are not in T.
But in the outer world it works, right?
Right.
Yeah. Okay.
But then we would need to add something to set f.
Okay. Well, it is just for
Yeah,
intermediate
it's
technical.
exactly the same
But
claim.
a general, a
It's
more
exactly
general
the same
statement
claim,
holds.
but yeah. So actually, maybe another way, maybe even better way of proving this main lemma would be to state something like that. So for every formula,
As it's general, yeah.
yeah, for every formula is equivalent to the statement of the disjunction of the corresponding lambda I.
This is how one
Provided-
can say that the Kripke model is actually simulated in theory T. Actually, it is kind of
Yeah. So that's basically what we want anyway. So that's what we essentially obtained by having proved our lemma up to the construction
Okay.
of phi I. So that's not a big deal. But okay, we are proving it in this more let's say historic truth to the history argument. So let's finish the proof in this way. So what I'm saying now, so what are we? So we are claiming the probability in T of that thing, so not the thing itself, right? So provable in T. So that's important because we will not be able to establish in lambda W.
such a thing
Without-
unless
without
you
T.
generally.
Right. I don't believe so. So and, yeah. Okay. Anyway. So let's see how it works. So first we remark, okay, so firstly we of course know that without any condition T proves disjunction of all the lambda x's, including 0, including everything there is in W. So T proves disjunction lambda x, or x lambda. So that's one thing. And therefore, it also proves box of it. So it is also provable in T. Secondly, we have that if V is not in R of W, then of course T plus lambda W proves box not lambda V. So for all the nodes which are outside this cone R of W, we have negation, provable in T. That's condition number 3. And condition and item 3 here is that the induction hypothesis, right? So T proves F implies conjunction not lambda x, where x falsifies phi I. So if in some node x phi I is false, then by the induction hypothesis for phi I, we have that T plus lambda x proves not phi T of phi I. So that's joining all these x's into one big conjunction. We have that. Or in other words, we will have that. So that means that x must be, well, we have lambda x for some x from W, but this x cannot be where phi I is false, and it cannot be not above W. In other words, it can only be in Fi, because Fi is precisely those where these two conditions are satisfied. It is phi I is true in X, and it is above W. So in other words, this means that this implies disjunction for X in Fi and X. Yeah, I've written this slightly incorrectly. So, of course, induction hypothesis delivers for us this, but then one would need to add box on top of it, right? So T proves box T F T phi I implies conjunction of lambda x false phi I that we have. And then taking together 1, 2, and 3, this in this form, we obtain that T proves box T F T F I implies this.
Yeah.
As required. So that's a more accurate description of this argument. But again, basically this is just the kind of expected consequence of the commutation conditions for phi I that we have. So, good. Right. So let's finish the proof of main lemma now with this claim out of the way. So let's prove. Right, but now it's more or less clear. So item A. So A. So suppose W in W this triangle is true. So we need to prove that T plus lambda W proves, so we need to prove T plus lambda W proves that Ft of phi 1 triangle T Ft of phi 2. That's what we need to establish. But, okay, so this is a statement of conservativity. We call that this is something for every pi formula. If box T plus something, if phi is provable here, then it's provable here. Something like that. Phi provable here, then it's provable here. Well, anyway, there everything occurs inside box. So we can replace f of phi I by this formula. So it is sufficient, this is equivalent by the claim to the following, disjunction for x in f1 lambda x, disjunction for x in f2 lambda x. So the meaning of the claim was to reduce this thing to this thing. So we did. Okay. Now, how do we prove that? Two cases. So suppose F1 is empty. What does it mean that it is empty? So if F1 is empty, means that nowhere the formula phi 1 is true. Nowhere above W phi 1 is true. Right? So phi 1 is false above W. But then here we have the empty disjunction. Empty disjunction is bottom. And bottom proves any formula, so anything is conservative over bottom. So disjunction bottom. Otherwise, it is not empty, and there is some u which is in F1. So we pick this u, and F1 are those x's in which phi 1 is true. But we assume that the formula phi 1 triangle phi 2 is true in W. That means, in U we have phi 1, and this means that there exists a V such that U has W V, and in V we have phi 2. Right. Automatically this V will be in F2. Right, because S, it connects only the nodes which are above W, so there will be a W, an R arrow from W to V, and V validates phi 2, so it's in F2. So that's nice. So we have okay, V is in F2, and then we have our wonderful condition. So then we have that lambda u implies triangle T lambda v. Recall that these conditions, this condition, USWV lambda T plus lambda W proves lambda UT lambda. So assuming lambda W proves lambda U triangle lambda V, and then we just weaken it to what we actually need. So then it also proves lambda U triangle disjunction for x in F2 lambda x, because V was from F2, and we replace theory by a weaker. And then, and this holds for all U in F1. Right, so for all U in F1, we have this. It means this holds for again by monotonicity of conservativity. So that's this is okay. So that's positive part of our lemma. So item A. So let's go to item B. item B. It's more or less the same. So item B. So suppose we have phi 1 triangle phi 2 is false in W. That means that there exists a U in F1 such that for all V in F2 not U as W. Is it visible from here?
Maybe you can close the door so that you can have more space.
Let's close the door. Right, so it's formally what it means that phi 1 triangle phi 2 is false in W. So there is a certain element U in which phi 1 is true, in this F1, such that there is no S related to V in which formula phi 2 is true. Okay. And so we have arrived at this set of all so F2 will be our set V from the condition, from the difficult condition A5. So that's the idea. So by A5, we have nt plus lambda W. We have not lambda U.
Well, I'm sorry. I guess in that implication, in the first line, you're using that symmetric definition, actually, as far as I can see. Well, because the definition only mentions that if phi 1 triangle phi 2 is going to be refuted.
If it is false in W, it means
then there is
a U.
Okay, it is the trivial part actually. Okay, yeah, yeah.
Right. There is
the equivalency actually is needing the, but you don't need it.
Right. So
it still holds. Actually, the other direction also holds.
Yeah. Okay. But anyway, so
yeah.
Now from condition, so we fix our U, and for V we have this F2. And then we obtain this, that not lambda U in triangle interprets disjunct for V from F2, lambda X, lambda V. So we have that. Right. And again, by monotonicity now, we can weaken this lambda U by to a disjunction of all possible lambda U's like that. So it means that it will also be not disjunction of lambda U or lambda X, let's say lambda X for X in F1. And that's it, because we again appeal to the claim and infer by the claim this about the interpretations of Fi. Replace this by, so this is equivalent to under the needed assumptions. theorem is proved. So at least we now have convinced ourselves that the conditions work. It's time for us to stop, but maybe I will still present the function without proving anything about it, but I will just disclose the secret, so to say, of the whole construction. Because, once you know the secret, in this case it's not totally obvious how everything should actually work, but the main secret is, of course, to invent this function. So let's the secret is to invent the function. Right. And there are certain adaptations to the standard Soloway construction. So again, we are going to define a function g from omega to w, like a Soloway function, so only one function will be in play here. But now it will react not only to proofs of statements lambda x. So as before, lambda x is the limit of g is x. So that's as it was before, which is good news. But we also need some other kind of statements, namely the statement delta w u of n, where again this w and u are related nodes. And this statement is roughly the following. On interval from n to infinity, rather like that, the function g jumps directly from w to u. So we are perceiving this function g as a kind of movement of a point through our keyframe. And this sentence is the following, formalizes the following, that, well, at a point n, our function g was at w for some reason. And then sometime in the future, g actually goes directly from w to u without making any further movements.
Mm-hmm.
You see, so that's so how do you formulate it? Very simply, so you just say that there is a t bigger than n, so g of t is u, and for all z t, something like this.
So this doesn't guarantee that g on n would be exactly w. It can be somewhere a bit below.
It guarantees. No.
Well, your formal definition doesn't.
Well, it doesn't guarantee. It doesn't tell anything about where g was before n. Could be also in n.
No, on n itself also it does not guarantee that g of n would be w exactly. It could be somewhere below w. Well, your formal definition at least doesn't tell anything about the valuation of g over n.
Let's do it like that. Let's do it like that. just to be sure, let me
But still,
write. Mhm.
okay.
What's the problem?
Yeah, okay.
Like between
No,
every-
in fact, we could actually say that this is
Yeah.
this is all.
In 2 minutes or
Right. We're living in 2 minutes. Yes. So it actually tells you that it jumps somewhere else.
Okay, yeah, I got it.
has to
Okay,
be-
my
it
mistake.
has to be-
You were right.
Well, I guess we need to finish, so we will not be able to write anything down. But the idea is that now, instead of looking at the proofs of not statements of the form not lambda x, we will be looking at the proofs of lambda x or lambda x implies delta. So these deltas will be kind of weakening, allow us to weakening the statements we will be reacting to when moving through this frame. But okay, how this mechanism works, apparently we need to postpone.
So, thank you very much. Could I ask you a very brief question?
Yes?
Maybe you could answer it in another time. So, why logics of P1 conservativity and of interpretability coincide?
Coincide? They coincide under
coincide,
under certain conditions, but there is a theorem which is called Poynting-Hayek theorem, which shows that the functions coincide for essentially reflexive theories. So like P8. So it's a theorem. It's not a simple observation.
But do we have a simple explanation of this fact or not?
No. It depends what you call simple, but no. It's a theorem. It's a well-known theorem. So like that.